Like the single peak preferences, now we are going to look at a different domain restriction which is quite related to the single peak preferences, but slightly different. This domain is known as the task allocation domain. As the name suggests, that we have one task, divisible task in this case, which can be allocated among the n players that we have. So each of these players get a share of that task, which we are going to denote as SI. So SI is the share of agent I, and this naturally lives within this interval 0 to 1, and sum of the task share among all the players is going to be equal to 1. So this task is always going to be allocated, so there is no part of this job is unallocated, and each of these agents get some non-negative amount of share of this task. Now, what is an agent payoff? We are going to assume that each of these agent has some most preferred share of the work. So for instance, someone likes the 50% of this job to be assigned to it, and anything more or less will be less preferred to it. Some other agent may have a different peak, so it may like 30% of the job, and anything more or less will be bad. So how can we motivate this kind of a task allocation domain? So you can imagine that these tasks may have rewards, or maybe it has wages per unit time. So let us assume that if a specific agent works for this Ti amount of time, then it gets a constant wage for each unit of that time. So WTI is the total wage that it gets for working Ti amount of time. But at the same time, the agents have some amount of cost for working. So for instance, it could be physical tiredness, or maybe less free time, or whatever it is. And this cost we are going to, let's say, assume it is quadratic. So there is a multiplier Ci, and as time progresses, the task gets harder and harder. So together, the net payoff in a very linear way, we can write it as the wage that this agent gets minus the cost it incurs. So this will be Ci, as we have defined. So Wt minus Ci square is the net payoff that this agent gets. So you can plot the payoff. So payoff on the y-axis, and on the x-axis, if we plot Ti, then you can see that it has a convex shape, and it certainly has a maxima point. So this maxima point is achieved at Ti star, which is given by this. So you can imagine that this preference with respect to time, or the share of this task, is essentially a single peak. So there is exactly one peak which it prefers the most because it maximizes its payoff, and anything more or less will be less attractive to this agent. So one way of pictorially depicting what is happening here is to draw the total task among different agents. So let's say we have agent 1. It has, so the total task can be shown on the y-axis. So this is 0 share of the task and 1 share of that task, and maybe there are some n number of agents here, and each of these agents have a most favorite share of this task. So maybe this red dot is showing that how much they prefer the most, and this can vary according with respect to different agents. And the total task, so the finally we'll have to divide the task in such a way that this dotted lines, which is the share of this task for among all the agents, they sum up to 1. So this amount of task is nothing but Si if this is agent I, and these are their peaks, which they prefer the most. Alright, even though this is single peaked, it is not exactly the single peaked with respect to the definition that we have used in the previous module. So where the single peakness was, if you can order all the alternatives, it was a single peak with respect to that. Here it is single peaked, but it is on the share of the task for each of these players. So how can we actually distinguish? Let's look at this example. So suppose there are two alternatives which are 0.2, 0.4, 0.3. So there are three agents. This is the share that happens to this is the share that is given to each of these players, and the second alternative is 0.2, 0.6 and 0.2. Then player 1 actually likes both of them equally because the share that this agent gets is exactly the same. So there is a certain amount of indifference. So these two alternatives are indifferent to player 1. This kind of a preference, two alternative being equally preferred, is not allowed under the single picked preferences. So this is single picked with respect to each of these shares, while in the earlier case we could have ordered all the alternatives in such a way that according to that common ordering of these alternatives, people had single picks. So we are going to denote this domain of task allocation with this notation T. So now our social choice function is mapping this task allocation domains for each of these players into this set of alternatives. So the notation that we are going to use is this Fi of P, which means that what is the share that agent I is getting, and the sum of all these FIPs summed over P, summed over I, should be equal to 1. Now, as before, we are going to use this peak PI, which denotes that which is the most preferred share of the task for player I. Now, since we have indifferences here, so we have defined the notion of Pareto efficiency even in the previous modules, in the previous settings, but here we'll have to define it a little more carefully. It's slightly different. So the social choice function F is Pareto efficient if there does not exist any other share of the task that is weakly preferred by all of the agents and strictly preferred by at least one. So remember in the previous setting, the single picked setting, it was that if a specific alternative is dominated by some other alternative by all the players, then that dominated alternative is never going to be picked as the social choice outcome. That was the definition of Pareto efficiency. Here the alternatives are essentially share of tasks. So we'll have to look at a specific share of task where we can actually find another share of task which is weakly preferred. So all the agents prefer at least as much as the current alternative, and one agent prefers it strictly better. If that happens, and then we say that this social choice function is not Pareto efficient. So the definition of Pareto efficiency means that there does not exist any other alternative such that that alternative actually is weakly preferred than the current outcome by all the agents, and there exists some agent for which that is strictly preferred. So this is strictly preferred. So let us look at some of the implications of this task allocation domain. So how can we actually make sure that this is Pareto efficient? So what are the most natural things? So the sum of the peaks. So the peaks are arbitrary, and therefore we cannot say that whether that sum of these peaks should be equal to 1. So if that happens to be equal to 1, then then the allocation problem is very simple. One can give each of these agents their favorite share of this task, which is Pi, and that will be uniquely Pareto efficient because nobody would like to change that. Anything more or less will be less preferred to them. Now, what happens if the sum of these peaks is more than 1? So that means if we try to allocate the tasks, which is this task such that everybody gets their peak, then we will be over allocating. So the sum of this allocated task will be more than 1, which is not possible. So then there must be one agent who gets less than its peak. The allocation is less than its peak. Now let us ask this question: can there be some agent J such that its allocation is more than Pj, more than its favorite share of the task if this social choice function f is Pareto efficient. The answer is no, because if you have, so we already know that there exists at least one agent who gets less than its peak. Now, if you give someone more than its peak, it also hates that. This agent J will hate that. Rather, both of them can transfer some of their shares. So this agent would be better off because it gets now a little more share of the task, and because it is single peaked, it is moving towards that peak, and that will prefer that more than its current allocation. Similarly, because this agent is also shedding off some of its task, and it is also moving towards its peak, which is Pj, then it will also be happier. So F cannot be Pareto efficient if these two things happen. So there cannot be any agent which got more than its peak, and therefore we can conclude that for all, under this condition, that is if the sum of these peaks is more than 1, for every agent the allocated share of the task should be at most Pj, cannot be more than that. And similarly, you can use the argument to show that when this sum is less than 1, the share of the task should be at least Pj. Okay, so the anonymity property that we have discussed before again applies here, but here the definition of anonymity is also slightly different, as we saw in the case of Pareto efficiency in this context. So the overall idea here is that if the agent preferences are permuted, so you are permuting the names of the agents, meaning that their preferences are permuted, then anonymity says that the shares will also get permuted accordingly. So if you look at a specific permuted agent, so the agent J has been permuted, and the new agent, the permuted agent, became sigma of J. And you have also looked at the P of sigma. So P of sigma is nothing but you have exchanged those columns. So you have a favorite peak, and it is monotone decreasing. So that particular agent has actually moved its the preferences. So that if that is the single peak preference over the share of this task, when we have permuted the agents, that means now a different agent, a permuted agent, gets that kind of a preference, while this agent gets something else. So that is P sigma once we have permuted that. If you look at the share of that permuted agent after their preferences are also transformed, this will be the same as the in the original game before permutation, whatever that agent J was getting in the original preference profile. It's best to take a look at an example to understand this point. Let us come here. So suppose there are 3 agents we have. So after permutation, agent 1 becomes 2, 2 becomes 3, and 3 becomes 1. And the original preference, original peaks were 0.7 for player 1, 0.4 for player 2, and 0.3 for player 3. And after permutation, now what happens is that because now the third agent is now the new agent 1, then agent 1's peak will be the agent 3's peak in the original game, so which was 0.3, that will come here. Agent 2 is the first agent, so that is 0.7 will come here, and agent 3 is the agent 2 in the original game, so its peak comes here. Then what anonymity means is that if you look at the original game, so here we have written the right hand side first and the left hand side on the other side. So if you look at player 1 and look at the original preference profile, that should be equal to the permuted one. So 1 gets permuted into 2 and the corresponding permuted profile. And this should hold for all J. So in fact, this is not all. We can write down this for all these agents. So F2 of the original preference profile will be F3 of the permuted profile, F3 of the original profile would be equal to F1 of the permuted profile. So we can write it accordingly. So this inequality should hold for all j in N. So let us now look at what could be some candidate social choice functions which are Pareto efficient and also anonymous. So the first thing that we can immediately think of is serial dictatorship. We have already discussed dictatorship. Dictatorship was in the context of alternatives which had only one specific alternative. There was no share, so there was no component for each of these agents. But here we are actually dividing shares, so it means that a predetermined sequence of all these agents will be given at the very beginning of this game, and each agent will be given either its peak, which is the most preferred, so they will come in sequence and they will pick their most favorite share, which is their peak, or they will get a leftover share. So if the sum of these peaks is less than 1, then the last agent will be given the whole leftover share. So notice that in this context, in this discussion, we are only focusing on deterministic mechanisms, and we are not going to discuss randomized mechanisms. Randomized mechanisms are those mechanisms where the outcome is random. So you do not give a deterministic share of the task or deterministically pick one alternative. Rather you pick that with certain probability. So we are not going to discuss that because those discussions are much more difficult, and the characterization in those domains are much more difficult than deterministic cases. So primarily we'll be discussing in this course only deterministic mechanisms. At the end we'll see that they will give some pointers to some randomized mechanisms. So serial dictatorship is a deterministic mechanism, deterministic social choice function. It satisfies Pareto efficiency. Why? Because if you look at the sequence, none of these agents, so because the first n-1 agents have actually got their peak share, or as long as the shares are available, and they will never like to exchange anything. So anything more or less will be worse for them, so therefore they will not like to change. There is no allocation which can improve their preferences. For the last agent there is no choice, and because that's the last agent, nobody no other agent, agents who are coming after that agent who got the leftover share, they will also not like to have their share, and also the agents who are coming before that agent, they will not like to change their allocation either. So it is Pareto efficient no matter whichever order of this serial dictatorship you choose. It is strategy proof because none of these agents now have any reason to misreport their peaks, because if they are coming in the beginning of the sequence, they will get their share, their most favorite share. If they come after the share is over, or only the leftover task is pending, then they don't have any choice. They cannot change it by misreporting. So the best response for each of these agents is to report their peaks truthfully. But what you can observe is that this mechanism is not anonymous, because there exists a predetermined sequence, and all the shares are written with respect to their names. So if we change the permutation, or if we rename them, then the predetermined sequence will still go with respect to that ordering, which are the numbers. And because now the agents have been switched and their peaks have been switched, so therefore they will now get a different allocation. So the allocation does not remain the same, and that's why it is not anonymous. You can think about it a little more carefully, and you can figure out that this is not anonymous. The other allocation could be something like a proportional allocation. And if we have something like P, sum of this Pi is more or less than 1, then we can actually either give more share to all the agents or less share to all these agents. So we can overload. So if we can give something like a C times PI, C times their peak allocation in this proportional method. So if sum of this PI is less than 1, then C will be more, so that means everybody will be given more than their peaks. And if sum of this PI is greater than 1, then C will be less than 1, that means everybody will get less than their peak share. Now the question is whether this is anonymous, Pareto efficient and strategy proof. You can easily argue that this is going to be anonymous, Pareto efficient. So this anonymity is coming because of the same constant. So we are either overloading or underloading all the agents in an equivalent way. So even if we alter their preferences and also their names, then the allocation will not change. It will go to the same. It will go to those permuted agent in the same share. It is also Pareto efficient because everybody is either getting underloaded or overloaded in the same way. So any Pareto efficient allocation is either giving the more share for all the agents or less share for all the agents. So there is nothing like someone is getting more, someone is getting less, so that you can readjust and make everybody better off. So that is not possible. So this is also Pareto efficient. But what about strategy proofness? Now suppose we have a peak which is 0.2, 0.3 and 0.1, right? So these are the agent peaks for these three players, and then you know that C is going to be 1 by 0.6, that is just 1 by sum of this their peaks. Now player 1 will now get 1/3 of this task. So because C is 1 by 0.6 and player 1's peak is 0.2, so it gets C times its peak, which is 1/3. Now this is going to be more than its share 0.2, which it likes more, right? So 1/3 would be more than that it likes. So 1 by 5 is something that it likes the most. So can it change its preference report? So it can actually, this is very easy to see that it can actually misrepresent its own peak such that the C gets altered accordingly, and then in that case, so C times 0.1, you can actually have 1 by 5, which is 0.2. So by misreporting its preference, its peak, agent 1 could get a better allocation, a better share of this task than what it is getting by reporting it truthfully. So this mechanism, even though it is quite fair, it is allocating it, everybody are underloaded or overloaded in the same way, this mechanism is not strategy proof. In the next module, we are going to look at a very interesting mechanism which is strategy proof.